Hi everyone, this is Ray Zhu. I'm going to present our work called IRISformer, which is dense vision transformers for single image inverse rendering in indoor scenes. This is a joint work between UC San Diego and Qualcomm AI Research. IRISformer is a model based on dense vision transformer to solve inverse rendering tasks in both single task and multitask settings. Specifically, given a single real-world image, the model infers material represented with albedo and roughness, geometry as per pixel depths and normals, as well as per pixel spatially varying lighting using spherical Gaussian mixture. Due to the nature of dense vision transformers that each image patch attends to all other patches in self-attention reasoning, we show that the NERD global attention enables us to implicitly reason about long-range interactions between different regions of the image, leading to better results in downstream applications like virtual object insertion, especially in challenging lighting conditions. Take these two indoor scenes for example. They're both comprised of diverse geometry, spatially varying materials, and complex lighting. To better model the complex lighting effects, including shadows, highlights, and interreflections, and give globally consistent and physically coherent estimations, transformers are well suited because of their global attention mechanism, as we just explained. Motivated by these factors, we propose to use transformers in place of CNNs as backbone architecture. There are two lines of work that are mostly related to ours. First is inverse rendering for indoor scenes to produce per pixel estimations or volumetric lighting with a CNN-based design. Another line is dense vision transformers, or DVTs, for depth estimation and semantic segmentation. In this work, we will harness the power of DVTs for inverse rendering tasks. We adopt a two-stage pipeline in our design. Specifically, in the multitask design, the input image is fed into a shared transformer-based encoder-decoder, and four output heads independently estimate the four modalities. Alternatively, in a single task design, the encoder and decoder are not shared. In the second stage, a similar design is incorporated to estimate lighting. Taking these outputs, a lighting renderer renders a per pixel lighting map on which we may impose a fully supervised lighting reconstruction error and an image re-rendering error constraining all estimations. Our model is trained on our OpenRooms dataset, which is a large-scale collection of photorealistic synthetic images of indoor scenes. We first evaluate our model against a CNN-based baseline from Lee et al. In this sample with strong highlights and complex scene geometry, we achieve much better estimations in all modalities. For example, on the ground area and the chairs, our results are much more spatially consistent with less artifacts and more details. Quantitatively, we achieve improved results in both multitask and single task settings, where the single task model is more accurate at the cost of more computation. To evaluate how our model generalizes to real-world images, we achieve the state-of-the-art on the IW dataset using the metric WHDR for measuring relative albedo. For geometry, we measure errors in depths and normals on NYUV2 dataset. We generalize better to less common objects like the printer in the first thing or the standing whiteboard and trash bins in the second thing. A third comparison is done against the most recent inverse rendering work of Wang et al. Lighting in the first sample is extremely challenging, and our model better decouples lighting from materials and geometry. To compare lighting estimations, we employ virtual object insertion by inserting bunnies into selected locations. In the first sample, the center bunny is properly lit up by our method. In the second and third samples, the lighting estimation is more globally spatially consistent across bunnies in multiple locations, in both the lighting intensities and directions. We also carry out a A/B study using the insertion results, showing more people find our results to be more visually convincing than baseline method. Material editing is another way to evaluate lighting. The first example showcases lighting from occlusion, where the second example has complex lighting on the wall from multiple ceiling lights. Our method is able to capture these lighting effects and faithfully recreate them on the new material. Finally, we may visualize the NERD attention maps of one patch with respect to all other patches. This further proves that our model captures long-range attention across the entire image frame. Also, notions of semantics like objects and material parts are implicit in NERD. Thank you.